Hello, everybody.
Hello.
I am starting with second lecture of analog filters. So
Okay.
we are now ready to spend some time for a second lecture of filters. Today we will talk about filter approximation. After New Year, I will have new slides in English, but this before New Year in 2020, I still have these slides in Croatian. So it will not be problem. I will write everything down in English on my workbook. Okay, so before all, we will consider two examples. If you remember, last time we were starting to speak about passive filters, and then we had one example, which is like this. Probably you saw it already. So this is called here is voltage source V1, or let's say V in. Here is we measure V out voltage. R1, C1, C2, R2. So this guy is called passive RC filter. And we all know how to calculate it. The transfer function of this filter, do you know how to calculate it? What is your answer? You can write me. Do you know how to calculate transfer function? V out over V in of S. Who knows? Let me show the message. Who knows? Or who is that?
I think firstly we have to write the impedance of C2 and R2 in parallel.
Yes, but this
Then
is
C1 and the other.
This is more easy to calculate with nodal equations. I will just write the equations and then you will know. Just one step, only one step. So if you write node 1, node 2, and this node here 0 is grounded, then we have nodal voltages. Nodal voltages are voltages from node 1 to grounded reference node 0, and from node 2 to grounded reference node 0. So we have for node 1, V1, 1 over R1 plus SC1 plus SC2 minus V2 SC2, which is equal to V in over R1. And for the second, we have minus V1 SC2 plus U2 V2. In English is V, in Croatian is U. 1 over R2 plus SC2 is equal to 0. So this is it. From this, now you can very quickly obtain the transfer function, which is in the form. So you just try to solve it. For example, from the second one, you have that V1 is equal to let's say 1 over S plus 1 V2, and V out is equal to V2, and then you have the following transfer function. So it is S R2C2 S square R1 R2 C1 C2 plus S R1 C1 plus R2 C2 plus R1 C2 plus 1. So this is what you have to obtain. So this V1, it comes here, and then you can calculate it. So this is something what every student knows how to calculate. And then in the next step, we must compare it with some general form of this kind of filter, which is K times S square plus omega P over QP, S plus omega P square. And then in the numerator, you have omega P over QP times S. You have the same. And then if you compare these two, then you will have omega P is 1 plus R1 R2 C1 C2 square. Then you will have QP. You can try to calculate it. It is not very hard. R1 R2 C1 C2, and then here you have R1 C1 plus R2 C2 plus R1 C2, and then you have K. Then you have K, which is equal to QP R2 C2 over R1 C1. Here is 2. Okay, so this is example of passive RC filter. And then we have second example of active, pardon, it's not active, it's still passive. We will learn active filters in the new year. Passive RLC filter. Probably you remember it from the last time. This is the one which looks like this. We have to write them, and then we'll compare what is going on. Here, LC1, C2, R. So this was the example. If you look at these two guys, this guy is Z2, and this one here was equal to Z1. And then you can solve this more simply. V out over V in here has the form of Z2 over Z1 plus Z2. So this was the what one of you thought for the first example. Okay, and then when we calculate it, then we have the following form. We obtain, after some calculation, S square LC plus 1 S square L C, here is C1, C1 plus C2 plus S L over R plus 1. And then we can also compare it to the general form, S square plus omega P over QP plus omega P square. But here is K times S square plus omega 0 square. And then we have the following quantities, omega P. So you can compare it. You can divide everything by L C1 plus C2, and then you can compare. And here on the left side, you can divide everything by R1, R2, C1, C2, and then compare. And you will obtain omega P is 1 over square root over L C1 plus C2. QP is equal to R C1 plus C2 over L. Omega 0 is 1 over L C1, and K is C1 over C1 plus C2. So we have these two examples, and we ask ourselves where are the poles. In the left side in the example 1, and in the right side in the example 2. The basic difference between these two is that this second one has L, and the left one doesn't have L. He has only R and C. Okay, so what is our point now? If we look at the first example, we will have to try to find the position of poles. But before all, we try to calculate how it looks like with the value of QP. I will change the color. To find it, we try to write 1 over QP, which is equal to R1 C1 plus R2 C2 plus R1 C2 over this R1 C1 R2 C2, which is equal R1 C1 over R2 C2 plus R2 C2 over R1 C1 plus R1 C2 over R2 C1. And if we try to write for this guy here to be equal to X, then this one here is 1 over X, and this guy here we can write as epsilon, which is small number. And then we have X plus 1 over X plus epsilon. Okay? So this is 1 over QP, and we try to find how this function f of x, how this looks like. I can plot it up here, f of x. You can check this function, x plus 1 over x, how it looks like. It looks like this. It has minimum value of 2. So everybody knows how this function looks like. That means this part here is, I mean, this function is always greater or equal than 2. So this part here is greater or equal than 2. And if we add epsilon, then we have another which is greater than 2. So if 1 over qp is greater than 2, then qp is smaller than 1/2. And this is very important limitation in this first example. In the second example, qp can be everything between 0 and infinity. Depends only on the values of R, L, and C. So this is something what we now found very important. If you have only R and C, then your QP is smaller than 1/2. If you have R, L, and C like here, then your QP can be everything. It can have also, we can write QP can be larger than 1/2 or whatever can be. So this is the conclusion of these two simple examples. Now we will see what will happen with the poles. If the poles have pole Q lower than 1/2, you can use some other pen. Poles, they look like this. So they are negative and real. Let's use more green. Where are the poles here? They can be conjugate complex. And that's important. How this affects our characteristics. So we'll start here on the new layer. If we look at the characteristics, if we have poles like this, for example, if you have only negative real poles, then the characteristics in the low pass case will look something like this. Not very, very strong. This is A of omega. If we have a combination of complex conjugate poles like this, then in the case of low pass filter, we will have much better characteristics, which is called selective. This one is selective characteristics. So which one we want? We want this one. This is not very useful. And now comes another example of band pass filter. This is low pass. Here is bandpass. In the example of bandpass filter, how we obtain bandpass filter? We start from low pass. Then we have transform low pass to bandpass, which is instead of S, you write S square plus omega 0 square over BS. Then you obtain bandpass. This is goal. And then this was, for example, first order. Here you obtain second order. If you start from second order, you will have fourth order. And so on. So this transformation is very known, and it's called low pass to band pass transformation. Okay. Now we see if we have low pass like this, and we put the transformation here, we will have bandpass like this. S square plus omega 0 square over BS plus 1, which is equal to S square plus BS plus omega 0 square, and BS goes up. And if we compare it with the general form, which is S square plus omega P cross Q P S plus omega P square K times omega P over QPS, we will have omega P is equal to omega 0. Where is omega 0? Omega 0 is this one here. From B is here. So we have omega P over QP equal to B. And K is equal to 1. This is also B. Or we can write the following form, that QP is equal to omega P over B. This is also important equation. Now we try to plot the characteristic of bandpass. So we can also split into two parts. The bandpass characteristics look like this. For example, it can have the form. Here is the magnitude characteristics has maximum equal to K, which is equal to 1. This here is omega P or omega 0. They are the same. And then we have at the position of 1 over square root of 2, we have bandwidth B. So this here is B. Okay, here is omega lower, omega higher frequency. And then the question is, if this B is for QP, which is, for example, lower than 1/2, how it looks the characteristics for QP, which is equal to 1/2? It will be the green one. It will be little bit more narrow than the first one. So this one here, this is B. B prime is for QP equal to 1/2. And now, what is the next problem? I will plot it red. How can we obtain very narrow characteristic, which is even more narrow than the green one, the red one? So this red one must have narrower B, which is for QP. One moment. This is for QP smaller than 1. This is for QP higher than 1/2. So now we have a problem. If we cannot have the QP higher than 1/2, then we cannot obtain narrow characteristic. And this is something what makes problem with our filters. So very often we need characteristics which is narrow. So this one needs QP which is larger than 1/2. And the same will be with band stop, with these guys. For the band stop is the same problem, because by band stop it looks like this. And more narrow one. And even more narrow one. So this is the also problem by band stop filters. So the problem can be solved only if we have poles which are conjugate complex and they have QP, as we saw, they must have QP larger than 1/2. Then we can save this problem. I will use green one. And then we can save this problem here. So what we need are complex conjugate poles. So we can pair them. We saw before that this is possible only if you use R, L, and C. Okay, here I didn't plot the characteristics. Here on the left side, this is, you can recognize immediately. From here, this is bandpass. And from here, you can recognize this is band stop. So this band stop characteristics, it looks like this. And it can be very narrow. Here is omega 0. Here is K. But this on the left side, this is bandpass characteristics. And I will plot it here. And it's very wide. Here is also K. But as you see, it has very large B. B is very, very high value. Okay? So the reason for this is not the position of zeros. The reason for this is position of poles. Here you have the poles which are negative and real, and the QP is lower than 1/2. And here you have complex conjugate poles. Okay, you have 2 zeros here because it is band stop. Here you have only 1 zero in the infinity, in the origin. Here you have 2 zeros in infinity. But here you have conjugate complex poles. Depending on the poles, you have possibility to have more narrow or more wide characteristics, or in the same time you can have more selective characteristics. So this is the reason why we need poles that are complex conjugate. I hope I was now I explained it very simple. Okay. Now we continue with our slides. We start with new paper. Okay, now I will translate very simple. This is contents, and this contents is telling that how we start with projecting of analog filters, and then we'll say a few words about Butterworth and Chebyshev approximations. We'll start with projecting or design of analog filters. Design of analog filters. What we need will be seen on the next picture. So you don't need to read this text here because it's not saying anything more than it must be defined by something what is called specifications. Specifications. And the filter must be of lowest possible order, feasible, and stable. Okay, this specs it looks like this. For example, specs for low pass filter design looks like this. So what we need to do is to fit the curve of the filter here inside. So it must be better than these points here. Okay, so now we have to design filter. Here on the left side on the slide is bandpass. here on the right side is low pass. So here is band pass. Okay. So now we start with our design. Then in the next step, we can apply some transformations. Here are possible transformations like low pass to high pass, low pass to band pass, low pass to band stop. So we had on the now just seen how it works when low pass is transformed to band pass. So you remember this s square plus omega 0 square over bs. Here is inverted bs s square plus omega 0 square, and here is omega 0 over s. So this is how this transformation looks like. Okay. This here left, this is called brick filter, which is ideal, and unfortunately we cannot make such a filter in reality. So to design such a filter, we will have to make some approximations. To make approximation of amplitude, this is amplitude, we start with characteristic functions, k of j omega. How we use them? K of j omega is a rational function of complex variable, and it must be, so we will call this characteristic function k of s n of s over d of s. These are polynomials in S or a rational function. Why a rational function? Because it has this ratio of two polynomials. It is this. Okay. Then what we want to obtain, our goal, is transfer function of the filter like h of s. Again, we have two polynomials in S. Okay, it is the same. Two polynomials divided by a ratio and its rational function. We must take care about feasibility and stability. Of h of s. Okay, so this is design. So we continue with Butterworth. Approximation. Why we call it approximation? Here is our ideal brick filter. and it is not possible to realize it. Then we will try to approximate it. So if we say that K of S is like here, if we say that this is C square, which is one constant, which we can immediately say that this is this. So if we say that K is equal to omega C to 2n, so this is like this, then we can write the H of S like this. Just a moment. And this is called Butterworth approximation. And this is defined with these two, K of S, and of course here we must put S equal to J omega. So K of S is something like this, and then absolute value and square. Okay, how this looks like? Omega C is called cutoff frequency, and N is called order. So I will plot here several Butterworth approximation. This is for example, N equal to 2. It goes here. This is called half power point. Because if the voltage comes to 1 over square root of 2, then the power comes to 1/2. Then we can see what is going on if we have higher order. For example, this is N equal to 3. And then higher order. This is N equal to 4, and so on. So all of them go here through half power point, or which is called omega C. And then all of them comes from here, and all finish in infinity in 0. So only in 3 points this approximates with 100% the ideal characteristics. In this point where it's 0, in omega C it doesn't. Everybody goes to 1 over square root of 2, and in infinity. So we can say only in 2 points, in infinity and in 0. And this Butterworth approximation is also called maximally flat. As you see, it here is continuous function. It's flat. Okay, maximally flat is some mathematical term, but we will not speak about this. Okay. Now we'll see what's going on with Butterworth? It looks like this. This is what I already have plotted to you. I can also use this move. So you see how it looks like. And then here are orders from 1 to 10. If you write in decibels, then you will have alpha is 20 logarithms of A. And A is absolute h of j omega, and alpha is then in decibels. Or we can write it like alpha is 20 log of absolute h of j omega decibels, so that we don't make any mistake. If we plot such a characteristics, then we have the picture on the left side. And then what is nice, then all these at high frequencies, they are becoming like lines. You see they are more straight than here on the right side. Okay, this is passband, and then here are the characteristics of Butterworth. Here at 0, it is the gain 1. This is this point here. Then of the point omega c, then in this point here, which is this guy here, is 1 over square root, and in infinity it is equal to 0. So this is then this one here. Okay, it's monotonic. It goes to 0 from when omega goes from 0 to infinity, and so on. What is the slope here? The slope here is equal to 20 times n dB over decade. This is slope at high frequencies. Okay. Now, how we calculate it, I will not go here into detail. So when somebody of you wants to learn it, I will show you where you can learn it. This is the derivation of the equation of the poles of the Butterworth filter. And here on this slide, we see that we always have to choose poles on the left side. The poles are on the circle. This is unity circle, and the poles lay in the left side. Okay. And here are the equations which you can use. So this circle has unity radius. This is 1, and this is equal to omega 0 of Butterworth. But the poles of the corresponding poles, the Q factors of the corresponding poles can be calculated using this equation. 2 sinus 2k minus 1 over 2n pi. Okay, so omega 0 k is 1. K is going to be 1 to n half, or n minus 1 half. This is for even, this is for odd, n. Okay? So this is k, and this is the equation how you calculate poles of the Butterworth filter. If you know poles, then you can design filter. Or instead of calculating, you can use tables. This is example of table of Butterworth filters for the order equal to 5. So here are imaginary or real parts of poles, or like this here, you can calculate Q, or you can immediately represent factors in the denominator. So this is something what you can find in some tables about Butterworth filters. The next approximation we will learn today is Chebyshev, and then we will finish. So it will be another, let's say, 10 minutes. And then I will be open for questions. What about Chebyshev? We will use new layer. If you use something what is called Chebyshev polynomials for the characteristic function, k of the nth order of j omega is equal to epsilon square Tn square of omega. Tn is called Chebyshev polynomials. And they are defined with these two parametric equations. What is parametric equation? This is like equation of the circle. For example, you have a circle like this, and this point here, it has x, y, here is x, here is y, and then you have phi. So x is equal to cosinus phi, y is equal to sinus phi. This is circle, and phi is parameter. Okay, so if you change phi, phi can be, let's say like this. Phi can be from minus 180 to plus 180, and then you have the whole circle. So this is called parametric presentation. Okay, circle. It is easy to see that this radius is equal to 1, but now it's not important. So if you change phi, it affects both x and y. So this is parametric equations, two equations with one parameter. Parameter is phi. Okay, like this is the same thing here. Here is parameter, this guy. So if you change this guy, if you change this guy, I want to get rid of this selection. I can delete it only. So if you change phi, like parameter, you obtain Chebyshev polynomials, and for different omega. Okay. Of course, arcus cosinus is defined for omega, which is inside these limits from plus minus 1. But if omega is larger than 1, then you have area CH. Don't ask me why. You can. This is also very simple derivation, but we will not show it here. Here is the recursive equations for Chebyshev polynomials, and here are finally Chebyshev polynomials. Okay, they can be calculated easy with this equation, but you must choose first these T0 and T1, and then you can calculate them. So this is very simple. Okay, now let me see how they look like. They look like this. And this is exactly what we need. We need characteristic function, which is for the pass band between 0 and 1, or minus 1 and 0, and for the stop band, which is going to infinity. Because our transfer function magnitude, in that case, because it is defined like this, if k is going to be 0, then h absolute is going to 1. This is pass band. If k, characteristic function, this one here, is going to infinity, then h is going to 0, and this is stop band. Okay, I will write it here. Pass band. And then these Chebyshev polynomials, they are not here 0, but they are near 0. Let's say they are 1 maximum, but this is okay. Or somewhere they are 0, like here. Somewhere they are 0. Okay. This is square. This is even better. We see that it oscillates between 1 and 0 for the omega from 0 to 1. So this will be pass band, and this k here will be going near 0. So this is pass band. Okay. So these Chebyshev polynomials, they are very, very good candidate for Chebyshev filter. Here are the properties, but this is something what we don't interest in. Amplitude frequency characteristic. So instead of kn, we can write Chebyshev polynomials, something like this. But we will write it as square. And because they go from 0 to 1, if we put some epsilon here, then they will go from 0 to epsilon. So this is better. Then we can adapt the ripple in the pass band. Here they say constant epsilon defines the ripple in the pass band. Okay. This is Chebyshev, how it looks like. You see something what is very interesting by Chebyshev. If we look at the previous slide, here we see Butterworth. So this is Butterworth. How it looks by Chebyshev. If we compare, I will plot it here. Then we have the black ideal one. then we can use the red one. And we can use the green one. And so on. What we have obtained, this is the ripple, and this was the price to be paid to obtain lower order. So because of this here is flat, and here is ripple. For this price, we have, this is Chebby. For this price, we have the most important thing, n, which is order of the Chebby, is lower than the order of the Butterworth. So this is the most important, which we have to remember if we compare Chebyshev and Butterworth. So here is Butterworth, here is Chebyshev. This Chebyshev has ripple and Butterworth is maximally flat. Okay? Here comes the properties of the Chebyshev filter, which is also very simple and very obvious. So you see properties of the filter of the Chebyshev approximation, n odd, n even, and then you have these values of the characteristics. This is for omega equal to 1, omega equal to 0, and omega when goes to infinity, we also go to 0 here. Okay? Here are the poles. The poles of Chebyshev here on the left, and if you compare with the poles of the Butterworth here on the right, so these on the left are on the ellipses. And those here on the right of the Butterworth are on the circle. So you see it now. Okay. If you want to calculate the poles of the Chebyshev filter, you have again equations. But this time it is not omega equal to 1. It is equal to some value, which is different than 1 because it is not on the unity circle, it's on the ellipses. And of course, here you have expression for calculating of pole Q's. And this phi is useful for the calculating of ellipses arms. Of course, you can also use tables. And this time tables have these omegas, which you can use to calculate poles and zeros, let's say poles, not zeros, of the Chebyshev filter. This is how it looks like if you change a ripple. If you change this here from 1 decibel, 2 decibel, or 3, then it also goes here down. So it's becoming more selective. And this is all for the Butterworth and for the Chebyshev approximation. There are many books and literature which you can use to learn about these filters. I will show you one of the books very quickly, but I don't know if it is good for you because it's creation. Maybe it's better to show you some English book. This is one of very good books. Schaumann, Valkenburg. You have PDF of this book in our website. Let me see what there is inside the book. So inside the book, you can learn about filters a lot. So you have such a book here on our web. So you can it is free. You can download it and learn from the book. Everything what we very short here show in these lectures, you can find it here. For example, 6. It is page 252. You have low pass filters with maximally flat magnitude. So let me go to this page 252. Let's say like this. Here you can learn everything about Butterworth, about ideal filter, Butterworth pole locations, low pass filter specification, and so on. So everything what I opened to you today, very, very concise and short, you can read here in the chapter 6. Ideal low pass filter. This is our brick wall. This is called here brick wall. You see my pen. Okay. Then you see Butterworth response, how it is calculated, and how you can see what is called maximally flat, and you can see the different order of the Butterworth, and then you can here learn how to calculate Butterworth pole locations. Here is the final equation which you can use. This is here. For example, of the third order, or whichever order, but you also can find the tables. So pole locations, and here is one example how you can calculate fifth order Butterworth filter. And that's it. Here is about specifications, how you can, this is page 261. You can see everything what I show in this lecture. Here you can see how you can define the order from low pass filter specifications. Here is the equation 644 of the order of the filter. This is important equation, and the derivation here. And then you have some examples here. You have a program something like PSpice, and this you can forget, arbitrary transmission zeros. You can forget it. And then next you have Chebyshev. About Chebyshev polynomial, this is chapter 7, page 277. And then you have everything about Chebyshev polynomials, about magnitude, and so on. Here is equation for the calculation of the order of Chebyshev. And here are equations. This is derivation of the equation how to calculate poles. This is page 284, location of Chebyshev poles. Here is example of poles on the ellipses and how you calculate it. And then finally, comparison of maximally flat and equiripple. You have it here on this figure. You see that the maximally flat is more it needs more higher order than the equiripple of Chebyshev. Okay. This is example of filter design, and that's it. This is everything what you have to learn for today. So this was chapter 6 and 7. Chapter 8, this is inverse Chebyshev and Kauer. This is something what we will very shortly mention next time. But for now, you know that you have to learn from the page 290 to the page 297, and of course from the page where it starts 252. So from 252 to the end of the chapter 7. So 6th and 7th chapter, you will learn everything in this book what we were talking today. And the book you have in materials on our website, like this, what I open in PDF. So this will be all for today. And we have learned how important are pole Qs, which are larger than 1/2, because we have complex conjugate poles. We showed 2 examples, and we said a few words about Butterworth and Chebyshev filters, but in details you can learn it only in the book. So this is all what I wanted to tell you today. If you have some questions, please ask the questions. Did you understand it all? Was it good lecture? So it was 2 hours today without pause, but it's okay.
Yes, it was clear.
Yeah, it was really clear.
Okay. If you have any questions, you can ask now, or you can send mail, or we can hear us using Teams or whatever, no problem. What is very important, this is all filmed and you can look it again and you can find the book on our website. So it was free. I found it somewhere in the internet. We will have the next after New Year. We will have another book. So you have 2 books in English which are very good. So it is enough for you, and not all. Of course, I will show you what are the chapters you will have to learn. That's it.
Okay.
Do you have something more to ask? If not, just send me mail. We will see us next Friday and at the same time. We will see, it will be probably 1 hour or 2 hours. I cannot judge, but I think it's enough. Today we were very long and that's okay.
Okay.
Thanks. Yes, perfect.
We'll hear us on the next Friday. Bye-bye.
Bye.
Bye.
Thank you.
Bye-bye.
Have a good week.
Bye.
Bye.
Also for you, all good week.
Thank you.